Another technique for solving quadratics. It's to use the buzz phrase of the century, a more flexible technique, and it works in all cases, no matter what type of question you're dealing with, whether the answer is rational, irrational, or even imaginary, so a negative under a radical, you'll get a solution using the completing the square approach, right? There are some types of quadratics that you just won't get a solution for if you use a factoring method, right? So you would need to use another technique. This is one of those techniques, right? So I made a slight adjustment. Again, this is page 31. So I made a slight adjustment here to the first step in each part of the process. But I'll take those as typos. Algebraically move the constant c to the right side of the equation is what that should say, right? Now you're like, okay, well, what on earth is a constant c? Well, if you remember from the beginning of our discussions involving quadratics, every quadratic in general form can be written as ax squared plus bx plus c, and then if you're looking for where it's equal to 0, you write it as equal to 0, right? But the expression itself is ax squared plus bx plus c. So the coefficient of the x squared term is your a. In this case, that would just be a 1. The b term would be the coefficient of x, and the c term would be the standalone constant. All right, so that first step is telling us to move that standalone constant over to the other side of the equation, but do it using appropriate rules of algebra. Right, so that's telling us subtract 9 from both sides. So I'm going to subtract a 9 from both sides, but I'm going to leave a little blank in its place. All right, so I'm going to leave a little blank, a little gap. All right, because what we're going to do is complete the perfect square trinomial. All right, for short, we call it completing the square, but what that means is that we're going to make an expression on the left side of the equation that will become a perfect square. Right? It may not be pretty, but it will be an expression that's raised to the second power. The benefit of doing that is based on what we were doing yesterday with the IXL, is that we'll be able to take the square root of both sides of the equation to find a solution. All right? You'll see that in a minute because that's a little bit like vague at this point. All right? But the process is really important because that's how we determine that perfect value to plug into the gap to make that perfect square trinomial. All right, so that's step 2. Add b over 2 squared to both sides of the equation and simplify. All right, so the b value, so b over 2 squared, the b value is 10 in this case. So I'm taking 10, dividing it by 2, and squaring it. 10 divided by 2 is 5. Squared is 25. This is a step that before too long I'd like you to be able to at least try to start doing in your head. Right? Yeah, it's a really useful technique, and even more useful if you don't have to write all these steps down. Right? Because it's a fairly simple formula when you really think about it. You're taking whatever the b value is, you're chopping it in half, and you're squaring it. All right, so I take a 10, cut it in half. What do you get? 5. Square it, 25. All right, do the same thing with like 24. 24, chop it in half. 12, square it, 144. It's not that bad. Yeah, it's possible you can come across some problems where it's a little crazier. All right, it's like, all right, 3,120, cut it in half. All right, well, maybe I'll get a calculator involved for that. You know, but for the simpler ones, you want to try to do it in your head. All right, so this number gets added to both sides of the equation. All right, so I'm going to add a 25, using a marker, of course, to the left side. But because I add something to the left side of an equation, I also have to add it to the right side of the equation. I could add anything I want to one side of an equation as long as I add that same amount to the other side of the equation. It's keeping the equation balanced. All right. So that's the second step. Well, almost. All right, it says simplify. There's really not much to simplify. All right, because on the right-hand side, that's just going to add to a 16. but on the left-hand side, we're going to have to factor that. I really should zoom in when I write. There we are. All right, so factor the left-hand side of the equation, which is a perfect square trinomial. All right, so this is the expression that I'm looking to factor. Now, it may seem a little weird that this process is supposed to replace the concept of factoring, and yet we're still factoring in using the process that's supposed to replace factoring. That's kind of a necessary evil, but there is a shortcut to the factoring process that I'm going to show you in a couple minutes. All right, but for now, if I want to factor this trinomial, it's always going to work out to be a perfect square trinomial, assuming you did this step correctly. All right, meaning these two binomials have to be identical. We still have the 16 on the right-hand side, but these two binomials have to be exactly the same. All right, so I'm looking for two exact same values that'll multiply to x squared, x and x. I'm looking for two exact same values that'll multiply to 25, 5 and 5. This trinomial is entirely positive, so our binomials should be entirely positive. All right. So this set of binomials, x plus 5 times x plus 5, can be written, because they're identical, as x plus 5 squared. We spent a lot of time in this course going the other way, where we would have an x plus 5 squared, and we'd have to distribute it out to get the x squared plus 10x plus 25. This is the reverse of that. This is getting us to the simpler way of writing x squared plus 10x plus 25 for the purpose of the next step, which is to take the square root. All right. But like I said, there is an easier way to get from that trinomial to the binomial squared. I'll talk about that in a couple minutes. All right. So number 4 is actively taking the square root of both sides of the equation, which means to include a plus or minus on the radical on the right-hand side, but we'll get to that in a minute. So actively taking the square root of both sides, meaning I am deciding to introduce a square root. All right, that's a natural progression of this process. The reason why we would do that is I want to get rid of that power of 2. I can take the square root of one side of an equation as long as I also take the square root of the other side of the equation. All right, I'm going to choose to take the square root of the left-hand side of the equation to get rid of this power of 2, leaving me with just the radicand x plus 5. But because I'm choosing to take the square root of 16, I have to account for the fact that that square root can be a positive 4, but it could also be a negative 4. All right, that's what one of the assignments yesterday was dealing with. All right, so we would put not just a 4, but also a negative 4. And the way we would represent that is plus or minus 4. All right, so plus or minus 4 means negative 4 or positive 4. All right, they mean the same thing. It's a shorthand way of writing it. All right, the plus over the minus is plus or minus. All right, so it's like you have a plus 4 or a negative 4. Or you could say you have a 4 that's either plus or minus. All right, they both would mean the same thing, logically. All right, so then we would write these as two separate equations. All right, I can make better lines than that. All right, so I would have x plus 5 is equal to negative 4. I'd have x plus 5 is equal to positive 4. And then I would just solve those two individual equations. All right, that should be the simplest step in the process. So subtract subtract 5 from both sides in both cases. And you get x is equal to -9 or x is equal to -1. Now this is actually something you could have solved by factoring, but it's nice to know that we have this new technique that'll also get the job done. Now you look at this and say, well, this is like 1,000 steps. Why would I ever do it this way? Well, if you have a choice in a matter and you can see the factors, you're looking at a trinomial and say, oh, I could factor this real easy, then yeah, I wouldn't do it that way. But you're going to come across situations where it's not factorable or you can't figure out the factors. Now you have a technique that you can use that'll kind of mitigate that. Also, there's the regions. They're going to tell you sometimes solve by completing the square, solve by factoring. I mean, it's the nature of an assessment. Sometimes you just got to do what you're asked to do. All right? But we're going to do a couple more because I want to give you a couple of different varieties here. All right? And also, there are ways to streamline this and make it not take 1,000 steps to complete. All right? So we're always going to get rid of that c value. All right, again, your quadratic's in the form of ax squared plus bx plus c. This one's equal to 0. Most of them are. And if not, we want to get them so that they're equal to 0. I'm going to add 12 to both sides to get rid of that c value, because I'm doing that algebraically. I'm going to leave a gap in its place. You could save yourself a step if you can complete the square in your head. All right? That's one of the ways to streamline the process. All right? Take the b value, cut it in half, and square it. All right? As long as you can identify what the b value is, and the b value isn't such, a crazy number, you should be okay there. I'm still going to write out the steps though. All right? So it's b over 2 squared. Because sometimes, you're given a formula, but if you kind of speak the formula to yourself, you can realize, oh, okay, it's actually easier to sort of do it in my head. You're like parentheses, b divided by 2, close parentheses squared. Yeah, that's a formula. But what is it really saying? Take the b value, chop it in half, then take that answer and square it. All right, so 6 chopped in half, 3 squared 9. That's what's getting added to both sides. All right, now the factoring step, that's what I mentioned before. I'd show you a little shortcut for that. We could do it the same way we did it before. You could always default to that, but there's a nice little nifty shortcut. When it comes to perfect square trinomials, the answer is always going to be a binomial squared. Now the right side is just going to be 21 when you add. It's always going to be a binomial squared. And since the factors have to be identical, you know that whatever the first term is of the first binomial has to be the same as the first term of the second binomial. Second term of the first binomial, second term of the second binomial, identical. All right, that's going to involve some square roots because that's the only way that that could happen. All right, if you think about what happened here, I can't find my, oh, there it is. The square root of x squared is x. The square root of 25 is 5. That's one way we could have got those values. So we use that idea over here and say, all right, well, what's the square root of x squared? What's the square root of 9? So x and 3, and then just carry down the sign of the middle term. All right, whatever the sign of the middle term is going to be the sign of your binomial squared. All right, so square root, carry down the sign of the middle term. And now you have your factored form. And you can cut out some of the fluff. So you can get to a point where if you don't have to show any of this, like just think about how much time and effort you're saving, all right? So I have x plus 3 as a quantity squared is equal to 21. Next step would be to actively take the square root of both sides of the equation. All right? So in doing so, left side, that radical is going to offset with the power of 2, giving an x plus 3. On the right-hand side, we'd have to look to see if there are any factors that are perfect of 21. There aren't. So we're stuck with a radical here. But we still need the plus or minus because we are making the choice to take the square root. So plus or minus rad 21. All right. Now, if you're not sure, again, you have the calculator to help you determine square roots, factors, and things like that. We always look in our table at, as a starting point, at half of whatever the radicand is. Half of the radicand is 10.5, so take 9. And then just start decreasing in value from there and just determine if any of these numbers will divide evenly into the radicand. Does 9 go into 21 evenly? No. 4? No. 1? Yes, but that's a trivial case, so that doesn't help. All right? So then we're stuck with that rad 21. Now we can do one of two things. And you got to be prepared for both, but I'll tell you which one I prefer and which one I recommend. I think it'll be obvious, actually, after I show you, but just in case. All right? So we can separate into two equations. X plus 3 is equal to negative rad 21. X plus 3 is equal to positive rad 21. My goal here is to get the value of x so I can subtract x from both sides. When we subtract a rational number from an irrational number, bless you, we want to put it in front of the irrational number. So rational in front of irrational, because it's really just a handwriting concern. Because oftentimes people will write their answer like this. Well, let me just really exaggerate it. Something like that, where anybody looking at it would be like, so is that radical 21 minus 3 like under the radical, or is that radical 21 and the minus 3 is separate? Like, what's going on there? All right, so to avoid that kind of confusion, we put the rational number first and then the irrational number. And then, slap the little or symbol there. All right? So that's one way you could represent your answer. But a lot of writing. Very explicit, though. Very clear as to what the answer is. Another way, or you have x plus 3 is equal to plus or minus rad 21. You could leave the plus or minus in, but this only works with radicals. All right, if you have an irrational answer, this is the only time you could do this. You can't do it with rational answers. Like, I couldn't leave my answers up here with a plus or minus in it because these are rational answers. But for irrational cases, I can subtract a 3 from both sides. Sorry, let me do that in blue. And write it as negative 3 plus or minus rad 21. All right. And again, that's because the plus or minus is the shorthand way of saying, well, the word or is in there, plus or minus. So it's a shorthand way of saying negative 3 minus rad 21 or negative 3 plus rad 21. All right. So I made a side example because I wanted to do one where you'd have a radical that actually needs to be simplified. On the next page, you have a set of problems at the top, 1 through 6. We're not going to do those, so if you wanted to steal some space there and write the solution to the problem we're about to do, you could do that. Or you can go to separate paper, whatever makes sense. So it's just a brand new side example. But we'll cut out a little bit of the fluff here. Again, we're going to get rid of that C value algebraically. Leave a little gap in its place. We're going to take our B value. We're going to chop it in half and square it. Do it off on the side here. And again, if you do that in your head, you could save yourself all this writing. I mean, it's not a ton of writing, but it's enough writing that you wouldn't want to do. And again, this is just side work. All right. So this is aside from the actual equation. You're taking that answer and plugging it into the left-hand side, but then also because you're adding it to the left side, you're going to add it to the right-hand side. All right. We could use our shortcut for factoring a perfect square trinomial. Square root of the first term, square root of the last term, carry down the sign of the middle term. Right-hand side simplifies to 12. Take the square root of both sides because we want to release the x plus 3 from the power of 2. Make it linear instead of quadratic. That's not a radical. Because we're making the choice to take the square root of both sides, we need the plus or minus on the right-hand side. But now we have a radical 12 here that we have to deal with, because that can be simplified. Radical 12 is the product of radical 4 and radical 3. Radical 4 is perfect, radical 3 is not. Well, radical 4 comes first, I don't know why I wrote that. So this is going to simplify down to 2 radical 3. So that's my substitution. It looks terrible. So x plus 3 is equal to plus or minus 2 rad 3. And then I'm just one little step away from my final answer. Because this is an irrational answer, I don't have to split the equation up. Subtract 3 from both sides. I get x is equal to negative 3 plus or minus 2 times the square root of 3, or 2 radical 3. And that would be it. All right. And so we get a nice, well, nice is a relative term, but an exact form of an irrational answer. If we put this into a graphing calculator and got a solution, the x squared plus 6x minus 3, I think I might still have it from before. These are the answers that you would have gotten. All right? So that's pretty, oh, not this one, but these are the answers that you would have gotten. This is a much more exact form of that. I mean, it is exact. These are just estimates. Right? So we would need this technique. All right, so what I'd like